Okay. All right, so I've been told to write larger, so I will scroll in larger letters. Okay, so I finished yesterday by mentioning fusion and how when we fuse a couple of quasi-particles, maybe of different types, fuse them together, it looks like one quasi-particle of some type. And furthermore, there may be more than one way to do so. And that's the origin of these interesting things, non-abelian statistics and applications in quantum information. Because those states are protected against decoherence, because decoherence involves local terms in the Hamiltonian, which we've seen can't cause transitions between these degenerate states. So anyway, I want to carry on and talk about fusion more. So I'm going to talk about the fusion rules and calculating the degeneracy of quasi-particle states, which I've already mentioned, but not been able to calculate. So as I said, if we have two types, alpha and beta, they can fuse to gamma, and they can do so in a number of ways, n alpha beta gamma, and this is a natural number. Okay, so there may be no ways to fuse to gamma, it just doesn't happen. There may be one way, that seems reasonable enough, and somewhat surprisingly at first sight, there may be more than one way in which they can produce the same gamma. And so we like to encode this in some formula, which is really just formal, very formal. So we'll just have some symbols, say phi alpha. And then we'll say that the fusion, possible ways to fuse alpha and beta, is represented by a kind of multiplication formula like this. So these are not operators, phi alpha, they're just symbols. In fact, I could have just not bothered with the phi and written alpha and beta. I don't know, but we like to write phi alpha. Okay. So these are the symbols. So what this says is that when I fuse alpha and beta, there are various possibilities. I can sum over all possible types gamma, which you remember we claim is usually a finite set. Here we're in 2 dimensions. We can sum over all of these, and then we have these coefficients, which might be 0 or non-zero, and possibly bigger than 1. Okay. And we will also say that this kind of product is commutative. This is the same as if I multiply phi beta times phi alpha. And so these are called the fusion rules. And now we're going to say some things about these in maybe no particular order. Basically, this gives us the structure of a ring on the quasi-particle types, or the symbols phi alpha, generated by the phi alphas. So we have various properties. First of all, we'll let alpha equal 0 be the trivial type, which we have which we create by doing nothing. And this is the identity. This acts as the multiplicative identity element. So that is 1 times phi alpha is just phi alpha, which means that n alpha 0 beta is equal to delta alpha beta. Okay. And we also have associativity, that fusing things in different orders gives the same result. Okay. So if we want to be formal about it, we can say that the set of phi alphas generates a ring, in fact a commutative ring, with an identity element. Okay. Okay, so one further thing we can say about this is we also mentioned that we should have an antiparticle for every quasi-particle. And so that means that there's some other object labeled, for which I'll call the label alpha bar, and the fusion of these two gives me the identity, and it gives me the identity just once. So if I pull that term out of the sum, then I have this. And so the surprise here is that the coefficient is 1 and not more than 1 or less than 1. Okay. All right. All right, so things get interesting if the number of terms on the right-hand side, the number of non-zero terms on the right-hand side here is bigger than 1, including the counted with multiplicities. So that is, if the total multiplicities for given alpha and beta, if the sum over gamma of the n alpha betas is bigger than 1, this is when things get interesting. This is when we have some degenerate states for the fusion of these quasiparticles or more quasiparticles. So this is when we get non-abelian statistics ultimately, or we may say we have a non-abelian system or non-abelian fusion rules. Question.
Is there anything that ensures that there's a unique alpha bar?
Yeah, there's something. I'm not exactly sure what it is, but it's unique. Yeah, thanks. Yeah.
Just to understand, so basically it's saying if you fuse a particle with its antiparticle on the vacuum.
You can get something else, yes. Yes, you can, in general, yes. And by the way, it's possible for the antiparticle to be the same particle, quasiparticle type.
You started last time, you were describing actual physical process of doing this fusion.
Yeah.
So does that process determine anything about, is it process dependent which particle you get when you fuse to?
Yeah, it may be, and it can depend on what else is present, in fact, further away. And that's not encoded in these rules. This is just the most general thing. And this is nothing about any processes.
Okay.
This is just, all this tells you is limited information. This is what you can get. Okay, and how many times happens to be important as well. But it doesn't tell you much about any kind of physics or dynamics, or they're not operators in Hilbert space. Another question. Okay, good question. So this is some formal sum that I've written here, which we will have to explain. Okay, but we'll see in a second how this works. Ultimately, I'll show you examples and and we'll get the results in other ways. And then at the end of that, and this is really how these things were obtained, you do something, you work with something that's more concrete, and at the end of the day you say, oh, well, look, I can summarize everything I've done by just writing these simple rules with this kind of formal addition, as well as a formal multiplication. So please just bear with me for that for a bit longer. Yeah. Well, there's only one identity. That's true too. Yes. So there's only one identity. So there's there's 2 points here. The first is that there's a distinguished element that's called the identity. Okay, and there is a unique identity.
But I think you mean when you untwist it. Yesterday you were saying the untwisting will just annihilate the original twist, which would suggest you would only have an identity. Right?
Well, but in fact, it depends on what else. That's true in the most simple case where there's only one object. When there's more things around, more things can happen. But this part may only come into play in a situation where there's more quasi-particles around, for reasons we'll see in a second. Yeah, if I get there.
Not intrigued about this equation. So when it's bigger than 1 gets none of the.
Yeah, if it's actually, let me make this a little bit more precise. If for some, not just some given ones, but for some, if there are 2 quasi-particle types, alpha and beta, such that this is bigger than 1, then we would say the system is not abelian. In other words, if it's only equal to 1, because we have to get something, so it's always, incidentally, the sum over gamma is not going to be 0. You can always get something by fusing, right? So either it's 1 or it's bigger than 1. If it's 1 for all alpha and beta, then we say it's abelian. We say we have an abelian system.
You don't have a possibility of having it smaller than.
No, because you certainly must get something, even if it's only the trivial object. Yes. Okay, was there another question I was in the middle of answering as well? All right. So let's. Okay. So now we can look a bit more at how we can use this to calculate degeneracy of states with some given quasi-particle types. So this comes back to various questions that were just raised. So one thing. So let's see. So yesterday I was describing having a basically infinite system, and we make this kind of twist operation to make a quasi-particle, or we do this several times to make several quasi-particles, and we can make one because we just twist around some point, and if you want to think of it as some string is there, even though the string can be moved around, the other end of the string is at infinity. So this is boundary conditions where we have infinity, and we don't pay much attention to what happens at infinity. But we may not want to allow those kind of boundary conditions. We may want to say that at infinity, there should be no net effect. Okay? Let's say it that way. And the consequence of that is that we can do the same thing as that if the system was compactified on a sphere. So if we have a sphere, then we don't have infinity, but we have, let's say, the South Pole. And we can't really have some ends of strings at the South Pole because those count as quasi-particles as well. So what we should do, well, we should count those things at the South Pole if they're there, maybe move them away from the South Pole. So what we should do is our boundary condition for these situations, for this kind of geometry, is that the total effect of all of the quasi-particles that we've created should add up to 0, so that we have the trivial boundary condition at infinity. So in terms of the sort of twisting operations, state at infinity should be unchanged. So that means that if we have several quasi-particles, we'll finally fuse to the identity type 0. Alpha equals 0. So we can draw a diagram for this, which we really learned from the string theorists, actually. So what we do here is we are going to introduce various quasi-particle types as these external lines coming in. We may start from some initial thing. We might think of this as the origin, actually, and then we add things at positions away from the origin. And so we'll start from 0, because where else would we start from? And with this boundary condition, so this is, if you like, increasing distance from the origin. And we can sort of look on a circle and see what's inside the circle and make the circle gradually larger. As we do, we gradually encircle additional quasi-particles starting from nothing. We encircle these, and eventually the circle is very large, and we're at infinity, and then we're now stipulating another boundary condition that at infinity we come back to 0. And so what happens is each time these lines meet, we are going to have to obey the fusion rules. So I'm going to label these gamma 1, gamma 2, and so on. And that's not 3 and 4, that's n minus 1 and n. So this is gamma n minus 1. So this last 0 is gamma n. And then each time we have these lines, we can attach to this the fusion coefficient n alpha beta gamma for those particular choices. But the gammas in the middle here are free choices. We can sum over all possibilities. So the degeneracy of the states then, maybe I should have started with a simple example. So for example, if we just have, well, the thing is, if I only have 2, I was going to do 2, but if we only have 2, it becomes a little bit too trivial, as we'll see. Let me do the general formula first. So the degeneracy of states associated with this is the sum over all the intermediate possibilities. And now you notice that because I'm in the first step, because I'm fusing 0 with alpha 1, then I can only possibly get alpha 1 here with one way to do it. Did I write this on the board? Yes, here it is. Fusion of anything with 0 gives me the same thing back. So alpha 1 is equal to, gamma 1 is equal to alpha 1. So I may as well only sum from gamma 2 up to gamma n minus 1, and then I can write a product of these fusion rule coefficients, gamma n minus 1, gamma alpha n, and gamma n minus 1, gamma n minus 2, alpha n minus 1, and so on. Let me go down here, n alpha 1, alpha 2, gamma 2, n alpha 1, 0. So I've written 1n for each vertex in this diagram. And the last one is just really a Kronecker delta, which I've already used here to put this gamma 1 equal to alpha 1 and eliminate it from the sum. I can just replace that by 1. So this is the degeneracy. And in fact, you'll see that if I only have 2 quasi-particles, then the only thing I have to sum over is uniquely determined to be alpha 1 and must actually be the antiparticle of alpha 2. But if I have 3, the same thing is true. There's only one way. And if I have 4, well, there could be n ways. I'm sorry. So let's do the case with 3. So this one here has to be alpha 1. So here I'm fusing alpha 1 to alpha 2, and I get some gamma, and I get a coefficient, which is n alpha 1, alpha 2, gamma. And then here I have alpha 3, and that has to fuse with this gamma to give me 0, the identity, and that coefficient is 1, only if alpha 3 is the antiparticle of gamma. And so the total degeneracy in this case works out to be just this single fusion rule coefficient, with the gamma replaced by alpha 3 bar. Okay, so if I have 3, then I just get the n alpha beta gammas. And if I have more than 3, then I have to calculate this sum. Now actually you can think of this as a matrix product. This is basically multiplying matrices. If you like I can remember which set of indices to focus on. Well, one is to say that the alpha i's here are some fixed labels, and then it's the gammas which are being summed over, and you see the gamma structure is just the structure of the index summation for a matrix product. Okay. In fact, this diagram might remind you of matrix product states from another subject. Difference here might be that in this case the internal labels are taking values in the same set as the external lines, whereas in matrix product states in general it could be a different set. Otherwise it's the same structure as a matrix product state. Yes?
So every equation is some consistency equation.
It's not a consistency equation. I don't know why you say that. This is simply a picture that describes how you use this to calculate the number of states. I don't think there's any consistency involved here. It's a consequence of the rules here. Okay? So when you have a product of things, of more than 3 things, you can then use all this data here to decompose it, to figure out, so this is what this is really saying is that this is, what I've written here is gamma alpha n times phi alpha n times phi alpha n minus 1 times phi alpha n, and the only thing is that I want this to, I want to pick out from here, I want to project this onto the final gamma being 0 because of this boundary condition at the end. So this is what I've calculated here, and I've dropped brackets because of associativity. So I've just taken a bunch of things and fused them, and this is just a diagram to help us visualize what we did in calculating it. If we take the brackets to be nested so that we take the product starting from the right, then we apply the formulas, then we end up with this formula for the total set of things, with finally this condition that the last thing has to be 0. Yeah.
The order of these fusions do not matter simply because they
In here everything commutes, so yes, the order doesn't matter here. This is just this formal fusion algebra. So it's not obvious from formulas, so it puts a constraint on the ends. The associativity gives me some condition on the ends, which is going to be some sort of bilinear relations between the ends.
So you use the fact that 0 using alpha 1
Yes.
gets
Gives-
rid of one of the sums, but
Yes.
you could also get rid of the last sum using the fact that gamma n minus 1 has to be alpha m bar.
Yes. Gamma n minus 1. Yeah, that's right. Yes. Yeah. No, we're not calculating any phases, any quantum mechanics. We're just doing some formal things here. We're not doing operators in a Hilbert space. Consequently, there are no phases. We're just doing some symbols, and we're calculating integers. Positive integers, that's all we're calculating. But this integer is the dimension of a space of states. That's what it is. Okay, so when we have the quasi-particles at some positions, well separated, and of these types, we get a space of degenerate states, and this formula tells you the degeneracy, or in other words, the dimension of the space, of the degenerate space, of the lowest energy states. Yeah.
Can you explain again why it has to boundary with 0?
Well, it's a boundary condition. That's the short answer. So there's a boundary condition at 0 or at infinity. So if I have at infinity, or at the south pole. Suppose the system is a sphere. Here's the north pole, here's the south pole. I could have a bunch of things on here. If I come from the top, see, a way to think of this in the plane is that if this is the origin, and then I start putting my quasi-particles in one at a time, then I can ask what happens if I look on these circles and just fuse whatever's inside the circle. In this case, if I have nothing at the south pole is the point at infinity on the Riemann sphere, when I get to the South Pole, I have to come back to 0 because there's nothing here, you see. And I have to complete this. I'm assuming there's no quasi-particle here, so this is another nice place where the state is nice and smooth. It looks like the ground state at the South Pole. So that's my boundary condition. Of course, there's nothing special about the choice of North and South Pole here either. So those are some of the conditions that are built into the structure. Yeah. Yeah, it's very much like that, yes. Let's not pursue it far. It's sort of, this is part of the structure of a generalization of that from groups to, for example, quantum groups. So that's one way that it arose. Okay.
Is there any relation to operator product expansion?
Yes.
Other conditions for the system not on the sphere but on the torus?
Well, not on the fusion rules, no, but there are conditions when we start constructing states and things. I'm only describing the fusion rules at the moment. There are some further structures, but that's not part of the fusion rules. Well, you know, if you really want to extend it to the torus, what you do is you say, okay, I have my quasi-particle types, but look, the thing that runs around here doesn't have to go from 0 to 0 for North to South Pole. Instead, I can identify North and South poles, and I can draw something like this. And then here we can, instead of having a boundary condition that we had there, we have a final index here, and we can sum over the whole thing. And then we can use that to calculate degeneracy of ground states on a sphere, or states with quasi-particles on a sphere, on a torus.
What would you get from here? Slightly different.
Well, this is the case corresponding to the sphere. This is the case corresponding to the torus. Okay. In fact, if you don't have any quasi-particles here, you just get a sum over the gammas, and this tells you that the number of ground states on the torus is equal to the number of quasi-particle types, which is a true fact. Okay.
Just want to make sure the equation calculates the degeneracy of the space.
Yes. Yep. Well, the ground state is unique. I mean, I guess there could be an empty set case of the formula where n is 0 and then we have one state. Maybe that's implicit. Okay. On the sphere, the ground state degeneracy is 1. Can we move on a bit? I think maybe we should postpone these questions. I'm not trying to cover everything on this board. You know, I have another 3 hours to go of lectures. All right, so what we've done here is we've used this setup with the fusion rules to calculate the degeneracy of a set of quasi-particle states, either in the plane, in an infinite plane with a certain boundary condition at infinity, or on a sphere. Okay. All right, so these are fusion rules. Now I want to talk about statistics. So I want to talk about dragging quasi-particles. So we'll define statistics by adiabatically dragging quasi-particles around until at the final time the positions are the same as at the original times. There's the same positions. However, we're allowed to permute the quasi-particles of the same type. Okay. So we may have more than one type of quasi-particle present. It actually doesn't make sense to exchange distinct types of quasiparticles, because there isn't a sort of well-defined gauge invariant way to define it. But when they're the same type, we can exchange them, and we can actually permute them by exchange. So you can only do permutations within the set of quasiparticles of each quasiparticle type. And when we do this, then we get, on the space of states just defined, on this degenerate set of states, let's just focus on the lowest energy state for the given set of well-separated quasiparticles. Then what we get is a Berry phase or matrix. The matrix will be a unitary matrix that depends on what exchange we make. That is, we get some matrix operation compared with the original state. And so what you could do is you could start with any state in the original degenerate set of states. You do some exchange, you get some state, and that's related to the set of those, or the space of those is related to the original space of states by a matrix transformation. And we have to do the exchange keeping these separations large throughout. Okay, now the effect of this exchange, this Berry phase or matrix, can depend on the path or paths taken. Okay. So it can depend on the path even when they're kept well separated. And however, the path dependence can take only a rather simple form. The path dependence can only be a phase factor, even in the case where the whole thing is a matrix. It's only a phase factor, and it does not depend on which other, if you like, quasiparticles are present. So, for example, consider a case where we just move one of the quasiparticles and keep the other stationary. The other cases are where we could move all simultaneously, but it's more complicated to think about, certainly. So let's imagine that we just move one quasiparticle with the others fixed. So what I'm saying is that there can be a dependence on the path that this quasiparticle takes. That is, it's not a topological invariant. If I make a small change in path, always keeping the quasiparticles separated, if I make a small change in path, the result could change, but only by a phase factor, and only by a phase factor that does not depend on what other quasiparticles are present and where they are. And so the form of that, and I'll explain in a minute why that's true. So the form of the phase factor, lets me consider that they're all moving and they move along some paths really in space-time. So because things are just exchanged, the paths can be kind of identified with loops. I guess I drew the worst case. So certainly if I just move one, what's going on here? Okay. So if I identify initial and final times, then I can think of this as a loop in in the space x, in space-time. And so if I parameterize my path with a parameter s, I could write integrals ds, but I'll just write them as dx. Then I get some phase, and I've included the contribution from each quasiparticle that may be moving, and I obtain I have an integral of a 1 form, really. So I have some phase factor, and to be actually more precise, since I can't always separate off this phase factor from the other part I'll talk about in a minute, what I really mean is that the change in phase, if I make a small change in paths, has to have the form of the change of an expression like this. So it's something where it just looks like it depends, it's a product of phases or changes of phase for each path, independent of what other quasiparticles are present. So this can depend, it depends on the path, and it depends on a quasiparticle type. Since they have to come back to the same type, we have a particular label, alpha, running around each loop. And so this can depend on the quasiparticle type, and it depends on the path taken, but it does not depend on what other quasiparticles are present. This, I guess, will probably sound much easier to swallow once I've given you an example, which will take a bit more time. That will come later. So, okay, but I'm saying this because from some people, you may get the impression that it's all independent of path, it's all topological. That's not actually true. They're not completely topological.
Runs from 0 to 2.
I'm not quite sure this morning whether I want it to be in space or in space-time. But so just take it as one or the other. So anyway, it's some geometric expression associated with the path, all right? Generally, these things will be independent of time, and I can just think of it, I can just project it down to be an integral in space. Okay, but for generality, we could have some time dependence. What? S is a parameter on the path, and I could write the integral as integral ds, but then I can also rewrite it in this fashion by a change of variable. Because geometrically, it's just depending on the path. That's the point. So the S would be the slow time evolution by which we evolve things. All right. Okay, so this is something which depends not on the other quasiparticles present, but on the background, on the background density of my system, perhaps, or on some other background fields that my system experiences. So it's a coupling to the background. Okay, so why does it have to reduce to this form, a phase factor which is independent of the other quasiparticles? Well, the reason is that if it did not, if I could make a small change in path, and so this change in path is basically, the effect is basically that I've gone around a little loop like this, and if this is small compared with the distance to other quasiparticles, this is basically doing something locally. And this is basically saying you're doing a local operation on the state, and this should not be able to detect the presence of other quasiparticles or which of the degenerate states you're in. So the only change to the Berry matrix that this change of path can make is a phase factor that doesn't depend on anything very interesting. It only depends on these backgrounds. I was trying to give you a minute to absorb what I just said. Other quantum numbers. You mean, well, the only things we're talking about are quasiparticle types. I don't want to worry about the quasiparticles have some internal spin or something. That's right, yes. Yeah. So that would factor out. So there would be something that could depend on that. Okay. All right. So it's not true in general that this thing has to depend only on the topology of the path. All right, so now let's turn to the part that depends on the path, on the topology of the path. So these small deformations of paths don't affect which way the quasi-particle goes around other quasi-particles. So deformations of a path of this type lead me to the idea that there are equivalence classes of paths, or of exchanges, which are more properly called braids. There are equivalence classes, or in topology these would be called isotopy classes of braids, let's say. So a braid, while it might be something complicated, it might have this goes here, this goes here, this goes here, something like this, something complicated. This might be alpha, this might be some different types, beta, that could be different. This would have to be the same. Maybe I lost an end somewhere. No, I don't think so. All right, 1, 2, 3, 4, 5. Okay. So some sort of diagram like this, where I'm allowed to finally permute quasi-particles of the same type, would be a braid. And so in the sort of obvious way of drawing pictures, I can deform things, and keeping quasi-particles well separated at all times, this is basically time going upwards, means that the lines in the diagram never actually intersect. And so I can deform the picture as long as the lines don't intersect at any stage. And this slightly unfamiliar term, isotopy, rather than the more familiar homotopy, is a version, if you like, is basically a version of homotopy, equivalence of things, where we actually build in the property that the lines are never allowed to intersect at any intermediate stage. It precisely, using that term precisely does that job for us. Okay. Otherwise, you can just call them topological classes of braids and imagine that you know what you mean. So the distinct isotopy classes are things that cannot be continuously deformed to each other in this way. So for example, if I use equivalence for isotopy equivalence, these two braids are equivalent to doing nothing, but on the other hand, a braid like this is not equivalent to doing nothing because I can't disentangle these braids, keeping, of course, the initial and final points the same. We're just changing what we do in the intermediate times. Okay, and we can't deform them without the lines crossing. Yeah. Okay, so now let's suppose now that all the quasi-particles are of the same type. All the ones present are the same type. And we'll use these pictures where we're basically taking the three-dimensional space-time picture and we're looking at it from the side. Or if we just take the configuration of quasi-particles at some time, we're looking at this projected onto a line. In other words, just looking at it from one time and intersecting it with some particular time slice like this. And if we choose the line carefully, then generically the points on the line don't coincide, and we can draw these pictures. So that's what we're using here. So, okay, so now we can draw some simple braids. For example, let's just do this one. N, or say I have n quasi-particles present. And so I'll say that tau 1, 2 is this, and tau 3, 4 is this, and so on. And tau 2, 3 is similar, and all the others are similar. And so in general, I have this set tau I plus 1, where I do this braid with this orientation on neighboring adjacent quasiparticles. Yeah.
Can you explain a little bit what does it mean for adding intersection to the line being comparable?
It means that I'm drawing a picture of something projected onto a plane, because that's all I've got. It's a projection of a three-dimensional diagram where lines don't have breaks in them and don't intersect. It's a very old, several centuries old convention for drawing pictures. Okay, it means that from the point of view of where I'm projecting, this line is closer to me than that line. I mean, the meaning should be obvious, really. And we have inverse operations where we go the opposite way in the same way. Tau I plus 1, I and I plus 1 are exchanged, but going in the opposite way. And these two are not equivalent or not isotopic. Okay. Okay, so if we start with this very simple operation where we just look at take a diagram like this, well, you just think about it in terms of the intersections or near intersections here. So then if you focus in like that, you get these basic operations tau. And from the pictures, as long as we deform things so that we don't have multiple lines trying to intersect simultaneously, we can obviously build up these pictures from these taus and tau inverses. And let's also point out that we can compose braids top to bottom. We can compose this with some other braid just by joining the lines in the middle. So we can do one braid and then we can do another following braid. And again, it's the same, the quasiparticles can be used among themselves of the same type. And so whether they're all the same type or not, the possible braids form a group. So because we have inverses, we can check associativity, and there we are. Okay. So we're going to try to argue that this group is generated by these taus and tau inverses, and there is going to be some relations in addition to the fact that tau inverse is the inverse of tau. So these relations are supposed to encode the isotopy equivalence. So one of these is that if I first do one of the taus and then another tau on a disjoint pair of objects, for example, just the following ones, but any disjoint pair, in fact, then we get a whole set of relations that it's the same as if we had done the other one first. Okay, so this relation is written as tau 3, 4, tau 1, 2 equals tau 1, 2, tau 3, 4. In other words, these just commute. Yeah. Well, I'm not even talking about amplitudes here. I'm not talking about the Berry phase. I'm only talking about these pictures. I'm only talking about isotopy classes. So at the moment, I'm not even talking about the Berry matrix. All I'm talking about is the structure of the group of braids, which is the isotopy classes. Yeah, it's different. We'll connect it in a minute. Well, that's kind of a definition of what you mean by statistical part of the matrix, but
Right, but the part that you didn't,
yeah.
part that you have not yet talked about.
Right. Well, I think I said that quickly. So yes, so the interesting part is going to depend only on the isotopy class. So due to the fact that the remaining part is so simple, it's just a phase, if we ignore phase factors, then we will arrive at the isotopy invariant interesting matrix part. And that's acting in a space whose degeneracy, dimension, is determined by the calculation with the fusion rules. So that's the setup. Yeah. I can't hear the end of that. Does it still depend on time, did you say?
The coordination does that
Still depend on path. The dependence on the path may become completely undefined if you let that length go to 0, because if it may depend on how many correlation areas are inside the path. If you let the length go to 0 with a fixed path, that phase can just oscillate and become undefined. So you have to be a little careful. You have to extract that thing before you can do anything else. But I'm in the middle of, right, let's not get diverted from the relations of isotopy. So in a minute we'll connect this with statistics. Just bear with me for a minute longer. So this is one relation that we can see from the isotopy of things, that if I exchange two objects and they're disjoint, maybe they're far away in space-time, it shouldn't make any difference which exchange I do first. Okay. So the second relation looks more complicated. Looks like this. So now we have exchanges involving pairs that are not disjoint. We have 3 of them, 3 objects, 3 exchanges. And isotopy means that I can move this line across the other crossing and end up with a diagram that looks like that. And if you look at this for a bit, you'll see that these can be deformed to each other. So this relation says that tau 2, 3, tau 1, 2, tau 2, 3 equals tau 1, 2, tau 2, 3, tau 1, 2. Okay. Now, of course, you can produce lots of other pairs of Braid diagrams that are isotopy equivalent. And incidentally, you should think of these not as just diagrams, but these might be little pieces of some more complicated diagram. Just look in some region, you may have something like this, and you're allowed to do this move. So you can generate lots of equivalent isotopy equivalences, but what we want to do is describe the structure of this group of braids. And so the braid group is named after R10 because in the 1920s he proved that the group of braids, for this case where they're all of the same type, so you can permute them all, is generated by tau I plus 1 and the inverses subject to the relations of the types of 1 and 2. Okay? Not just these particular sets of indices, but any disjoint pairs in the case of the first one, and 3 successive indices in the case of the other one. So these are the only relations you need to impose on these taus in order to get an abstract group which is isomorphic to the group that you produce by looking at braids which are viewed as equivalent under isotopy equivalence classes of braids. Okay, so that none of that was quantum mechanics. Okay, however, the application to topological phases may be clear, and that is that we can imagine these processes going on in space-time, and if we can remove or ignore these little path-dependent things, then we just arrive at information that is isotopy invariant, and so that will leave us with matrices or phases that depend only on the isotopy class of the braid, and they will have to obey relations. Each of these taus become some phase or matrix, and these will have to obey these mathematical relations as matrices, rather than, and whereas here they're just abstract group elements. So this group is called Bn for n objects. Okay, so I'll give you a little homework exercise here. It's sort of to think about group theory or to think about braid diagrams. If we impose an additional relation that tau I plus 1 squared is the identity in the group, in other words, tau I plus 1 is its own inverse for all I, then we just get the permutation or symmetric group Sn. So this is the group of permutations of n objects. In fact, this exercise might sound tough if you think of it as group theory, but if you approach it by drawing pictures and understanding what the pictures mean, then it becomes very easy. And so it's recommended for thinking a bit about these relations.
When Arsene proved the generators and relations result, did you already know about group Western groups?
I don't know. He was doing it in the 1920s, so you tell me. It's not clear to me. I mean, this is all part of the history of knots and links and things, so I don't know. Even though I've actually looked at Artan's paper, but I don't remember if, you know. Okay. All right, so as I was saying a minute ago, if we now want to move this into quantum mechanics and think of these taus as exchanges, then tau I plus 1 is going to be some matrix or phase, in fact, a unitary matrix. I wanted to say one more comment about just groups here, group theory. The Artan braid group is an infinite order group. It has infinitely many elements, and that's because you can just keep tangling up these braids more and more. They never sort of disentangle themselves, they just get worse and worse. So you have an infinite set of braids. Of course, the permutation group is finite, it has n factorial elements. Okay. All right, anyway. Okay, so these tau I plus 1s should become unitary matrices, and okay, and so to describe the braid group, to describe the effect of any braid, the matrix representing any braid, it's sufficient to know the matrix of tau I plus 1. And of course, the inverse is the inverse matrix. So that's the virtue of using generators for a group. Once you have the generators, you only have to know how the generators are represented as matrices. No. See the following example. So the simplest example where we can do this is we can take tau I plus 1 to be e to the I theta, just a scalar, independent of I. So this is why I can't impose determinant 1 on these. Okay, so that looks too simple. What if you plug this in here? Well, you see these relations are all just kind of homogeneous in the taus, so these are trivially satisfied by this for any theta. And if I want it unitary, then theta has to be real, so this has magnitude 1. And so this corresponds to what we call abelian anyons, or what were called anyons from about 1980. And now we refer to these as abelian anyons. So this is the simple case. Yeah.
Would you be able to take away those path-dependent parts? That's also like you split this case from the body?
Well, you know, you may have a little ambiguity in actually doing so in practice, but basically, as we'll see when I finally get to an example with the Laughlin state, that I think what we argue there is that, well, we know that there's a phase that's there when there's no other quasiparticle present, and we just take the ratio of these phases and we discover what the effect of the exchange is in addition. You know, in practice, that issue doesn't bother us very much, but it should sometimes be kept in mind. Okay. Okay, so, and all other cases, and theta, by the way, I should have said, so theta can be an arbitrary number. They're only different, it's only defined modulo 2 pi, of course, and so that's why they're called anyons, because it can be any phase. Okay, and you know, e to the I theta is +1 gives me back bosons, and e to the I theta is -1 gives me back fermions, and there we just have the, you know, the textbook description of statistics is you just talk about permutations of particles. For permutations of particles, you have the additional relation tau squared is the identity. So that means e to the I theta squared is 1. So e to the I theta is either 1 or -1 if it's abelian. So you get Bose or Fermi statistics. And textbooks assume that that's the only thing you're allowed. They assume it has to be abelian, and then they argue triumphantly that you're only allowed fermions and bosons. But the more refined point of view is that at least in 2 dimensions, you really have to exchange things adiabatically along paths and keep track of which braid you did, and then you get this more refined sort of classification, if you like, where you have other possibilities that turn out to be completely consistent. The other possibilities then being that these are non-commuting matrices So then you can try to construct these as matrices subject to the relations shown here. Ultimately, there will be some more relations. Here we're just talking about the Braid group part of the picture. There can be more relations, but it turns out that many interesting cases of non-abelian statistics survive these physical requirements and can exist. So then we have non-abelian anyons or particles or quasiparticles with non-abelian statistics. Okay. Yeah.
Is theta being irrational somehow a sick case?
No. Why? Why should it be? Well, that doesn't mean it's a sick case. As far as Braid group representations are concerned, it's not. But there are further requirements. And in particular, if I have a finite number of quasiparticle types, I ultimately end up with rational numbers. Okay. All right. So this is the picture with. So here we just talked about the exchanges, and we just talked about it so far with all quasiparticles of the same type. So we can extend this analysis to quasiparticles of more than one type. And so naturally what you get is some rather similar but a bit more complicated description. Yeah, okay. So in the general case, you can not only exchange quasiparticles of the same type, which will give you the same matrix tau as if they were the only quasiparticles present, you also have what we call mutual statistics, which describes what you get if you... I've messed up some pictures here. That's interesting. If you take one type, alpha, completely around another type, beta. If I went once, I would be exchanging them, but that's not really something well defined. I can exchange again, and I get back to the original positions. And so then I'm going to have some matrix, let's say sigma, for this kind of operation. And there are going to be some sort of relations involving these, which you can obtain in a similar way if you want to. So then you have mutual statistics, where you may pick up a phase or a matrix when a quasiparticle of one type goes around a quasiparticle of another type. Okay, now if we come back and remember that we also have fusion, then we can combine the two things. So fusion and braiding must be consistent. What I mean by must be is the underlying picture is that still that we're in a topological phase, we have quasiparticle types, and we're making arguments based on the existence of a gap, and the fact that if we deform things, we deform paths, we expect the results to be isotopy invariant up to those uninteresting phase factors I keep trying to throw away. Okay, so what we can do when we have fusion and braiding is I might have two quasiparticles of types alpha and beta and another spectator gamma. I can either take gamma around alpha and beta and then fuse alpha and beta and get some type gamma or delta or something, or I can fuse them first and then do the braid. And in space-time, I can deform the pictures into each other. So the pictures look something like this, which I think I have wrong in my notes. If I fuse, finally, then I have something like this. So let's say I have alpha and beta, and they fuse to gamma, and I have another one of type delta. Then, so let's imagine that gamma and delta are not the same. And even if they are the same, I can certainly consider this operation. And so the fusion is represented by this 3-point vertex, and this is homotopic to a picture where I first fuse alpha and beta, and then do the braid afterwards, coming back to the same place, delta, delta, gamma. So this is the kind of thing that has to give the same results. And so in terms of quantum mechanical amplitudes, there's some amplitude actually for fusion, which is not contained in the fusion rules, and I haven't talked about it, but there's some amplitudes for fusion. And these have to be consistent. And so these will give the same matrix because they're isotopic. And okay. And so with this kind of thing, you can consider this as quasiparticle statistics and fusion. So can this really happen in some physical system, say a topological phase? And this was basically discussed by various mathematical physicists, especially in the 80s, Doplicher and Roberts, Froelich, and other people in the 80s, who basically established that it's quite possible to have rich structures of these operations in what we might consider a topological phase in a quantum field theory. And there are some additional structures which I haven't mentioned. I haven't described all of this in complete detail. And in terms of these mathematical structures, the same structure was found in rational conformal field theory. Same mathematical structure. So this is Moore and Seiberg, 1989. So it's a very different context, but the same things of fusion. I think Leo asked me about conformal field theory and fusion rules. So the same structure of fusion rules and the corresponding amplitudes that I haven't mentioned, and also the braiding occurs in connection with rational conformal field theory. It also occurs in the context of quantum groups, and it culminated in the idea of a modular tensor category, which is Reshetykhin and Turayev, 1990, and also connected with Chern-Simons gauge theory, by Witten, and also connected with isotopy invariance of knots and links, which is Vaughan-Jones, about 1984. So this is some very nice, beautiful mathematical structure which involves a great deal of consistency relations and which is also manifest in these two-dimensional topological phases. Questions? Okay, so this is background to, or this was the background to what we did using conformal field theory. So now I'm going to start on proper quantum Hall effects. So now we go from modular tensor categories to semiconductor heterostructures. I know, yes. Okay, so quantum Hall effect occurs in a two-dimensional electron gas. These kind of setups can be constructed as semiconductor heterostructures or as quantum wells. I'm not going to say much about it. Just say things like aluminum, gallium arsenide. And then the Hall effect can be measured in a Hall bar, which drawn sloppily looks like this. We run a current through. The probes ought to be lined up a bit better than they are here. And then we can define the ordinary resistance. Well, the 4-probe way to measure resistance is to divide the voltage difference between the probes 1 and 2 by the current I, which flows between different leads. And the Hall resistance is the voltage difference between 1 and 3 divided by the current. So these are the basic definitions. This is what you actually use in the lab, unless you decide to do a 2-probe measurement. Okay. So let me just mention that the density in these systems typically, which I'll call n bar, the density, the number of particles per area in the sample, about 10 to the 11 inverse square centimeters. So classically, what you find in a simple model, well, basically in a model really, let's imagine there's no disorder, or anyway in some appropriate classical system, is that the whole resistance is a straight line, which is just B over n bar EC. C is the speed of light, not the central charge. N bar is the density. So this is the classical Hall effect. And classically Rxy, which is the same actually as the Hall resistivity rho xy, is the magnitude of the magnetic field over n bar EC. And this can be rewritten as B over n bar times E over hc, which is 1 over the flux quantum, hc over E, and h over E times h over E squared. H over E squared is a resistance of about 26 kiloohms. And of course, I'm using here some system of units. As you know, it's frightful trying to figure out units in electromagnetism. One person here took electromagnetism with me, in fact. Okay, anyway, so in some system of units, this is correct. And hc over E is the flux quantum. So this is what's appearing in this formula, if we want to write it this way. And then in the quantized Hall effect, it was observed experimentally in this semiconductor heterostructure at low temperatures that rather than the classical Hall resistivity or resistance, what you have is a sequence of plateaus where Rxy is constant to very high accuracy on the plateau and then sort of steps down like this. And the classical line would be this dashed line here. And furthermore, so this is a plateau, and Rxx is basically 0 as temperature goes to 0 on the plateau, on each plateau. And the values of Rxy on the plateaus correspond to sigma xy, which if rho xx is 0, sigma xy is 1 over rho xy. So for these things, you have to remember that this is a tensor, and you have to invert the tensor. That's why, yeah, okay. That's why it's relevant to mention rho xx. And so it's found that if I write it in terms of sigma xy, this is nu E squared over h. Where nu is an integer or rational, more generally rational number. So the integer effect was discovered by von Klitzing and the fractional effect by Stormer, Suey, and Gossard a couple of years later. And this nu we can think of as a dimensionless measure of density, basically by referring to what I wrote here, just by taking the reciprocal. So because of what I wrote there, which I suspect is what von Klitzing was writing in his notebook the night he discovered the effect, because he says things like that, that nu is the density times phi 0 over b. And so this is a dimensionless measure of density. It's basically density measured in some units that depend on the magnetic field strength b. And the flux quantum is something that turns that into the correct unit. So this is dimensionless. So at least nominally, this is what this nu represents. It's not quite the whole story, but it's not bad. And if we don't have disorder and we say some idealized things like that, then this is exactly correct. And we can think of this as not density per area, but density over, not number per area, but number n over n phi, the number of flux quanta in the system. So n phi is the area A times the magnetic field strength B over the flux quantum. So it's the number of flux quanta through the area of the sample. So that's what nu is. All right. Why what?
Why did Von Twister think to do this experiment?
Well, they weren't expecting to discover quantum Hall effect. What they were really doing was they were thinking that at low temperatures you get a Wigner crystal where the electrons crystallize, which is a rather classical kind of thing, actually. It's just they get stuck in some places because of the Coulomb repulsion, because the density is so low. So he was really expecting to see Wigner crystal or maybe some other, I don't know what else, but that was the only thing sort of expected at the time, I think. Or maybe Anderson localization. You remember, Charlie? I don't really.
Yeah,
I don't know.
Just they're using this new technology of making a two-dimensional electron gas.
Seeing what happens. Yeah. Yeah. In fact, the Wigner crystal you might have expected in the fractional case, but anyway, they weren't even thinking that far ahead at the time. Okay, so to think about this further, perhaps again following von Klitzing in one night in 1980, let's just look at the Landau level problem. So this is the single particle problem of a charged particle in a magnetic field. So let's say it has mass m sub e. And if I'm still using these horrible units, then my Hamiltonian probably looks like this. So it's P minus A. And curl of A is the magnetic field. And I'll think of the coordinates as being in 2 dimensions only. The magnetic field is perpendicular, but don't worry about that too much. And then the energy eigenvalues of this Hamiltonian are the same as for a harmonic oscillator. And omega c is the so-called cyclotron frequency or Larmor frequency, EB over mc. So in a magnetic field, the particles go around in circular orbits at a certain frequency, and this is the frequency. Okay. If we use the so-called symmetric gauge choice for A, since I'm going to write wave functions, I need a gauge choice. That's A is half R cross B. This is a rotationally invariant around the origin choice for A. Then the eigenfunctions, or choice of a basis for the eigenfunctions, taking the case n equals 0 for the lowest Landau level only, LL lowest Landau level. Each Landau level has a high, basically infinite degeneracy, or it's a infinite dimensional space of states, and the eigenfunctions in this space for the n is 0 case I'll write as z to the m times e to the minus a quarter mod z squared. And for normalization, we need 1 over square root of 2 pi 2 to the m factorial. So here z is x plus iy. And I've also set a certain length scale to 1, so that maybe goes here. The so-called magnetic length is defined as LB squared is h bar c over EB. So this is the area covered by a flux quantum within a factor of 2 pi. And I'm setting this length to 1. So then I arrive at these eigenfunctions. Okay. So these functions, um of z, by the way, I'm writing it as a function of z, and when I do that, I don't imply that it's holomorphic or anything, and this is obviously not holomorphic. It's not complex analytic. So um of z is a function which you can check as an exercise is peaked at, if I take the absolute value squared, you find that that has a maximum at mod z equals square root 2m. So these functions are angular momentum eigenstates or rotational eigenstates, and so this density is rotationally invariant. It's concentrated on a ring of radius square root of 2m. And from this we can calculate that the number of states in the lowest Landau level per unit area in my units is 1 over 2 pi. So I have one state per magnetic flux quantum. One per flux quantum per Landau level. And I find the same thing in the higher Landau levels. They're all basically the same, except, of course, that the eigenfunctions for the higher ones must be different because they must be orthogonal to these ones. Okay. So let me just try to conclude by saying something about how this relates to the quantum Hall effect. So the idea, probably realized by von Klitzing, is that if we occupy the lowest new states for new integer, so n is 0 to nu minus 1, nu is an integer, then the density is going to be not arbitrary, but it's equal to nu over 2 pi in my units, and it's uniform. It's uniform if I occupy them all in some region of space. And so then the filling factor nu is 2 pi n bar, and that's an integer. Well, I mean, we already know it's an integer, but the nu over there is the same as the nu here. Okay. So this, so as I've defined nu here, this is the same as the filling factor I defined over there, but the point here, of course, is that now we see that there's something special about the values when nu is integer, because we're filling an integer number of Landau levels. And once we fill an integer number of Landau levels, any excited state at the same particle number requires that I promote a particle from a filled to an unfilled Landau level, and that requires a minimum energy of h bar omega c. So my excitation spectrum for particles has, or particle and whole in this case, has an energy gap. So this is a system with an energy gap, as I've described it. It's a topological phase. And the fact that it's a non-trivial one is shown, for one thing, by the quantized Hall conductance. All right, so this is where I'm going to stop.
Questions before we take a break?
You mentioned something about a Hilbert space. I'm a little confused about what exactly is the Hilbert space.
Well, when I was mentioning the fusion rules, I said I'm not working in a Hilbert space. They're just symbols.
And someone asked, and you mentioned Hilbert once, but it was brief.
Well,
We need to know
Can't
what we're
answer
doing
it.
in quantum computation.
well, then we're doing it in Hilbert space, of course. Fusion rules tell us the degeneracy or the dimension of the space of degenerate low energy states. That's how it relates. That was the message of the part about the fusion rules. You can use that to calculate the number of states. And then the braiding matrices are basically matrices in that subspace of Hilbert space.
No more questions.
The next lecture will start at 11.
Do you know if there is a formalism like monumental category for the case when quasi